All right, so another video and another random number generator. So we're actually jumping in time a little bit more, and we're actually changing lanes a little bit. So if I go back to my little list that I was doodling around before, I mentioned we'll see a couple of these other ones on these kind of classic ones in some of the activities and homeworks that you'll see later. So we're going into this page a little bit of kind of what do we need to see for some of these, cryptographically secure ones. One of the bins that existed are these that are based off of some hard math problems. If you remember back into the intro video, I did say there are some of those ones that are somewhat easy to talk about, but they are horribly slow in terms of actual implementation. So that's the one that we're first going to look at is one of these ones based off of a hard math question, namely the notion of factorization. That will give us one of these processes that exist, from a theoretical point of view, but not good enough from an actual implementation side of things. So that one is down here. So emerged in about the 1980s or so, at least that's when the paper presentation of them, they kind of started to gain a little bit more steam in the later 80s, earlier 90s side of things. So this one's going to make use of basically squaring modulo n, repeated over and over and over and over again. The setup's going to sound very similar to like a setup for like an RSA crypto system. So you're going to grab two of your favorite primes, P and Q. You're then going to have some nice little number n, which is the product of P and Q. And then we're going to start with a seed value and then just repeatedly square that number over and over and over and over and over again. It's going to generate a sequence of numbers, just like the last couple have. And the idea is that they're supposed to be hard to kind of get a feel on what the next number is, as long as you don't know what the factorization of n actually ends up being. So here the idea is that if you actually can factor that number n, it's fairly easy to start taking some square roots modulo n. So the moment you have that, then this whole process basically explodes and becomes too easy. So that's where this one is then going to be based off of a hard math question. So as long as that notion of factorization is considered hard, so as long as we're living in the pre-quantum stage that we are right now, then this process, at least again, works from a theoretical point of view, but does not actually work from kind of a speed and useful implementation side of things. But it is still one that is kind of cute to look into a little bit. So hence the reason we're chatting about it now. So just kind of a really small toy example just to see it, I guess, kind of in action. Here I randomly grabbed a couple very small primes. So 313, which is this nice palindromic prime. So is Q, so 101. And if you multiply those things together, you get another palindromic number. So 31613. That thing is 15 bits long. So you can kind of see that we doubled the length of that by multiplying those together. And I'm going to hit this thing with a seed value of 23. All of the numbers in the backside are then going to be these 15-bit numbers. So I'm going to write them all in binary with 15 bits. So a whole bunch of zeros are going to be needed on the 23. But as we get into this process, that we'll start filling in with some of the other things. Obviously, storage becomes kind of annoying on this, is that we're going to start multiplying really big things together, reducing them modulo n, hence the reason why this becomes a very, very slow process. So one of the things that we need these random number generators to be is fast. This one is not that, but it's easy to draw up and it's easy to talk about. So 23 squared mod n, well, 23 squared is just going to kick out 529. So I actually don't need the reduction modulo n there because I was not yet large enough. But then when I take 529 and square that, it will actually generate a number that, is larger than my modulus n. So I get what? 279841. So you reduce that, it kicks out 26937. Take that and you square it. That starts to create much larger numbers. So that's where your storage side of things, even if your modulus is, n bits long, when you start working in it, you're going to have enough room to be able to double that because you're going to spill over and then reduce afterwards. So x3 will be that 26937 squared, creates a big number, reduce mod n, brings you back down to 2393, and then you keep that process going. I obviously got lazy and didn't want to draw out a whole bunch of those things, but they are totally there. For those of you that have or are taking my Math 436 class, we've chatted about some of these square root side of things. So you at least have maybe a little bit of additional insight information about kind of the underlying math workings of this system. For those of you that have not taken that class, I highly recommend it, obviously, because you get to look at some of the inner workings of those things. And then that process or that system, kind of the hardness of going backwards is a bit more obvious. But for now, we'll just kind of play around with some of the code to kind of see those numbers swirl around. So let's swap into my screen if possible. Maybe, man, struggling with the swapping of screens. So it might just be you explore it on your own kind of thing. So I hit swap, but I don't see a green bar around it. So that's making me think that it's probably not actually swapped into it. But that one's actually a pretty boring thing. It actually looks very similar to our linear congruence. So the way that you're going to generate your next number is just take x times x modulo n. Everything else is basically the same. So while I was not able to share screens, it's probably for the best because it was not overly interesting anyways. So I'll probably just pause this video and I'll I guess kill my Zoom session and restart a new one to make sure that I can swap for the next couple of things, because those are the ones that I want to be able to see some code and actually dance around. So you might be staring at the code right now and it's, actually working, and I just think it's not, but oh well. Anyway, I'll stop rambling. I'll let you click the link on D2L and see that process emerge, and we'll hop back into actually doing some of these processes through some hashing algorithms and start merging together this topic and our last topic and see some cool things emerge. Okay, back in, I guess, 30 seconds. Well, I got to take a couple minutes to actually kill things, but you can just go on to the next video and hopefully everything is still a go.